Hi, everyone. You ready for some carboxylic acids and nitriles? Those are the next two functional groups. We are now in Unit 3. So let's take a look at the key concepts. Unit 3, Part 1. Yep, new functional groups. So we'll talk about naming them, talk about some reactions that produce these functional groups, and then we'll move on and see what you can do with these functional groups, how you can change them into other functional groups. Okay. Carboxylic acids. I should have pulled up the IUPAC naming procedure and shown you the ranking of functional groups, but I think you already know, because I mentioned in past videos, carboxylic acids is at the top of the list. It follows a pattern that the more oxygen atoms, the more pi bonds, the more important it becomes, at least in IUPAC's eyes, right? So at the top of the list. There are a lot of common names out there, but I'm only going to require two, the two most common carboxylic acids. And we got the first one here, which you've seen since Gen Chem. We talked about titrating sodium hydroxide with vinegar. It's a standard lab in general chemistry, and we probably didn't draw the skeletal drawing of vinegar. We probably just gave the chemical formula, something like that, or like this, right? Those should look familiar. Anywho, now you know the chemical structure. You got the C double bond OH. If you want to give it an IUPAC name, there's two carbons. Carbon 1's here, carbon 2's there. Ethane is two carbons. And we're going to tack on ethanoic acid. But nobody calls it that. That molecule is going to be vinegar. It's going to be, well, it's not vinegar, sorry. It's going to be acetic acid. Vinegar is not 100%. Did I say that right? Vinegar is not 100% acetic acid. It's like 5%. And something like this has some other things in it too. Acetic acid is the name. Gosh, I don't know how long it's going to take for chemists to give up that name and go to ethanoic acid. Probably never. The other common acid you need to know is the one carbon carboxylic acid, formic acid. Form comes from the Latin word for ant. So you know those stinging red ants? Have you ever had an experience as that? If you ever encountered ants as a kid, I know I have. We'd be, playing out in the front yard, no shoes on, and we didn't know it. We disturbed an anthill, and all of a sudden we felt this pain coming from our ankles and realized, oh my goodness, all these red ants are stinging us. Yeah, and they're actually injecting this molecule, formic acid, into your skin. And ouch, it's carboxylic acid. Hey, acids are acids. So it's actually acidic. It's actually a weak acid, so it's not too bad, but it is annoying. So know that structure, and all you do is replace acetic acid's methyl group with a hydrogen. And you could draw the chemical formula like this if you want. That's probably the most common one. There we go. So know those two common names, formic acid, acetic acid, and you're set on my exam. As we start going over some examples of IUPAC names, I'll throw in some common names for those of you who are not in my class and just checking out this video. Kudos to you. Your instructor may require some additional names, some additional common names for you to memorize. And yeah, they're very common, so I can understand the reasoning there. All right, let's hit it. IUPAC names. Okay, so if you have a very complicated molecule, there might be a need, not on my test, there might be a need for a prefix for the most important functional group. But again, not on my test. If a carboxylic acid shows up in a molecule you have to name, you're most likely going to use the suffix because carboxylic acid is top of the list, most important. Identify it with the suffix, and it's oic acid, which is convenient because if you see the carboxylic acid, the ic acid group, ic acid, show up, put an O in front of it, you got oic acid. There are cases where you might have a carboxylic acid group attached to a ring. I'll do that example in a minute. And then you switch the suffix. We did the same thing in when we talked about naming aldehydes. Same pattern between aldehydes and carboxylic acids when attached to ring. Nitrile group. Well, nitrile is pretty highly ranked, so oftentimes you're going to use a nitrile suffix. Thank you, IUPAC. At least you did something logical there. If we're dealing with the nitrile group, let's use that word for the suffix. Cool. There are other times, like if it exists in a molecule with a carboxylic acid, where the nitrile won't be ranked number 1, and you can't use a suffix, then the prefix is cyano, and it's got a C and an N in it, right? And the nitrile group is a C triple bond N. So there's some logic here too. Cool. And I got something in from italics here. Yes, be very careful counting carbons. We'll do some examples to illustrate this. The trick here is that there's no C in the word nitrile. There is a C in cyano. So the short of it, the short point that's being made here, if you use the word cyano, that means the C triple bond N is an added group onto your parent. So you do not count that carbon of the nitrile as part of the parent. You do so, you count that carbon if the nitrile group is the most important group in the functional group, in the molecule. You're going to use the suffix nitrile to identify, hey, there's a triple bond N, and in that case, the carbon is counted as part of the parent chain. Examples, please. Right. Okay, we'll start again, top of the list, carboxylic acid. So if you need to name this molecule, you'd say, okay, what's the most important functional group? It's carboxylic acid, double bond O with an OH. And so we're going to use the oic acid suffix. How many carbons are here? I got 1, 2, 3, 4. Molly eats peanut butter. Butter reminds me of butane. I'm about ready to put the E in butane and remember, oh wait, is there a vowel on my suffix? Yeah, there's an O. So drop that E of butane and then add oic acid and we're done. Butanoic acid is IUPAC name. The common name is butyric acid. Molly eats peanut butter. Butter, yeah, the Greek word for butter is what gives us this base, what is that called? I don't know. the root of the word butyric, that's the word I'm looking for. Butyric comes from the Greek word for butter. And butter is a fat, one of the fats in our diets. Not a very healthy one, but it's a common fat found in butter. So anyways, butyric acid, actually, keep on going, more of a tangent, but kind of interesting. When butter goes rancid, the bacteria are breaking down the fat molecules and they actually release butyric acid or butanoic acid. And it smells horrible. If you ever smelled anything rancid, you know the smell. You know the smell of butyric acid. Gosh, it is a common name. You know the smell of butanoic acid. All right, what else we got? What if you have 2 carboxylic acids? Let's start with 4 carbons again. Let's just derivatize or change butanoic acid, and we'll put another carboxylic acid at the other end. Okay. Well, it's got 2 groups. What do we do when there was 2 methyls in a molecule? We use the prefix dimethyl. If we had 2 alkenes, 2 carbon-carbon double bonds, 2 enes, we said the molecule was a diene. Same thing here. We got 2 carboxylic acids. We're going to have a dioic acid. That's our suffix. How many carbons? 1, 2, 3, 4. It's still butane. That's the parent chain. I'm going to leave the E in here because a consonant, vowels and consonants. D is a consonant. So we keep the E in there if you're particular about those things. And we got dioic acid. Isn't that crazy? IOI. Yeah, don't look at it that way. It's di and then oic acid. Butane dioic acid. The common name, in parentheses, not on my exam, is succinic acid. That's an N. Cool. You might recognize that as, hey, then we have the succin somewhere else. Yeah, an NBS. So N-bromosuccinic succinamide. Yeah, there it is. N-bromosuccinamide. So we got 1, 2, 3, 4 carbons. This group comes from succinic acid. Gosh, I'm full of extra stuff today. Sorry. Let's make the long. Let's stay on point here, Dennis. Okay, so we illustrated how to name carboxylic acids using the suffix oic acid. If 2 of them show up, dioic. If 3, trioic, right? Ooh, let's not have that on the exam because then we have to capture the parent chain. And you can only get 2 of those. Anyways, gosh, thought I was going to stay on point. You're only going to see 2 carboxylic acids maximum on my exams. And that's pretty much it for carboxylic acids. They're going to be the most important functional group on my test. Oic acids, your suffix, and then add the extra decorations, right? There's chlorine here. Then the carboxylic acid's carbon 1. The chlorine's on 3. So just add your decorations, your extra prefixes out in front in alphabetical order. Always number from the carboxylic acid because it'll be the most important functional group. Okay, the one little goofball is what happens if there's a carboxylic acid on a ring. We saw the same predicament when we talked about aldehydes, right? So quick review, aldehydes cannot be in a ring. Why? Because that carbon that makes up the aldehyde, it needs 3 bonds to be an aldehyde group. This carbon has a double bond to an oxygen and a single bond to a hydrogen. So there's only 1 bond left. So this carbon cannot be a ring carbon. It's impossible to give this carbon 2 bonds to make it part of a ring. So IUPAC says, well, what's our rules for naming this molecule? Well, step 1, find the longest chain or ring with the most important functional group. Where's the most important functional group? That carbon, and it's not a ring carbon, it's a chain carbon. So then you'd be stuck naming this, hey, the longest, the parent is methane with the al group. Al is a suffix for aldehydes. So the parent name would be methanal. And then the cyclohexane ring is a extra group. On carbon 1 of methanal, there's cyclohexane. Ew, but what happens if you got a chlorine or something else on the ring? We're going to have a complicated name. So IUPAC said, let's change the rules. For aldehydes, if you have this extra aldehyde group on a ring, use a new suffix. So what's the parent? We're going to make the ring the parent. That's an L. Cyclohexane. Before I add the E, I think about what's my new suffix? It's not al, it's carbaldehyde. Ooh, and that starts with a C, a consonant. Carbaldehyde. And there's an extra carb in the word. So this reminds you, hey, there's 6 carbons in a ring of 6, but add a new carbon that's part of the aldehyde group. So we capture 7 carbons with this parent name. And now you're using carbaldehyde. That makes this ring carbon, carbon number 1. And we get to number the ring because the parent is cyclohexane, so it gets the numbers. And now we see that on carbon 3, there's a chlorine. Do the exact same pattern over here. Hey, there's a ring and a chain. So IUPAC would normally say, hey, who's the longest chain or ring with the most important functional group? Carboxylic acid, which can never be a ring carbon, right? This carbon, the carboxylic acid, is already maintaining 3 bonds to be a carboxylic acid. So the old way of naming this would say, oh, the parent must be methane, methanoic acid. And then we got the cyclohexane ring attached to methane with the chlorine on the other side. And that's not benzene, so I can't use meta. No, do not use meta here. That's not benzene. It's just a plain old cyclohexane ring. Okay, so then what do you do? IUPAC says, well, modify your name. So using al, we use carbaldehyde. So instead of use oic acid, use carboxylic acid. Cyclohexane, that's an A, carboxylic acid. And now in this parent, we got a ring of 6 carbons, and we got carb again, telling us there's a 7th carbon that's part of the carboxylic acid group. So we got the ring of 6 and that 7th carbon of the carboxylic acid. But now, with the suffix carboxylic acid, the ring carbon to which the carboxylic acid is attached is carbon 1. So the chlorine's over here on 3, and we got a nice, neat name, 3-chlorocyclohexane carboxylic acid. The name is way bigger than the molecule. Crazy. Okay, that's the only quirky, weird thing about carboxylic acids. Let's deal with the nitrile. Specifically, let's take care of this note in italics here. Yeah, clean page. All right, so let's start with the basics. What if you have a chain and then there's a triple bond in? I'll put it at the end. Okay, so you'd say, hey, IUPAC, what's your rules? Step 1, find the longest chain or ring with the most important functional group. C, triple bond end, is the nitrile group, and that's a suffix. So step 2 is identify the parent. Well, there's a chain of 1, 2, 3, 4 carbons. This is the nitrile group, and you know what? Maybe we can get in the habit of when the nitrile group's the parent, maybe this is the added on group that makes it the suffix nitrile. So we kind of don't include carbon. That's not the right way to say this. Count nitriles carbon with or in the parent. Meaning the nitriles carbon, the carbon that's triple bonded to nitrogen, is carbon number 1. So we count it. So there's 4 carbons in this chain. I think that makes sense. Sure, 4 in a row, 4 carbons, that's butane. Molly eats peanut butter again. Butter, butane. And I think about that E, well, what's my suffix? Nitrile. Ooh, starts with an N. Leave the E in there if you have to. I'm not going to take off points on my exams if you drop the N out. But that would look weird, 2 N's together. Anyways, enough said. Let's name this molecule. Okay, find the longest chain or ring with the most important functional group. Most important functional group is right here, the nitrile group. So where's the longest chain with this carbon that now is carbon number 1? Well, you can go down and branch left, or you can go down and branch right. They're both a chain of 3. So here's my parent. I'll go this way. 3 carbons. Molly eats peanut. Peanut reminds me of propane. The suffix is nitrile, so keep the E in there. Cool. And here's carbon 2, here's 3. Hey, this extra branch is on carbon 2. Cool. Oh, if you want to put in a 1 before the nitrile group, sorry, the nitrile suffix, or in front of the parent, you can, but it's redundant. The nitrile group, if it's showing up as the parent, it must be part of the parent chain. And again, that carbon's got 3 bonds devoted to the nitrogen. It has to be at the beginning of the chain if it's the most important one. So nitrile, if you're using as a suffix, it's always on carbon 1. So you can leave it out if you wish, or put it in there if you like. It's not incorrect. It's just redundant. It's like there's no other choice for the nitrile group, so you can legally, if you wish, if that's the word, leave it out. Cool. Okay, start again with this molecule, but you know what? Let's throw this group in here. Let's shake things up a little. Okay, so rules are, step 1, find the longest chain or ring with the most important functional group. Nitrile versus carboxylic acid. Carboxylic acid wins every time. This is carbon 1 of the parent. Okay, we're going to use oic acid. Yep, oic acid has a suffix. How long is my parent chain? Well, first, figure out what's your decorations to the parent. I have this thing, the triple bond end. The nitrile functional group, the cyano functional group, is a C triple bond N. So this is my decoration, my substituent, the added on molecule. And now we don't include the nitriles carbon in the parent. We're going to have to use cyano as the prefix, and cyano has a C in it. So it's understood that, hey, when you say cyano, you're identifying the decoration, the extra group as a C and a triple bond N. So my extra group is this C triple bond N, and that extra group, that extra C is not on the parent. So my parent chain is only 3 carbons long. And to that 3 carbon chain, there is a cyano group, another carbon attached to carbon 3. So on carbon 3 of the parent, there's a cyano group, there's a C that identifies this C, and there's an N, I guess, that identifies that N. And that cyano group is on a chain of 3 carbons, propane. Think about that E, what's my suffix? It's oic acid. Now, it makes more sense if the nitrile, why did I do that? If the nitrile group is branching off of the chain. So let's go back here, and now let's just add a carboxylic acid over here and name this molecule. Okay, find the longest chain of ring with the most important functional group, carboxylic acids on carbon 1. Go 2, think about going up to 3, but hey, that's my decoration. I'm going to label or identify the C triple bond N with the prefix cyano. And I can't include that carbon on the parent. So to make the chain as long as possible, I'll go out to here. Now I still have a chain of 3, that's propane. But now in carbon 2 is the cyano group. And so it's actually the same name as above, we just changed the 3 to a 2. And that might be the reason why IUPAC did this. It's like if you look at a catalog, hey, what are some molecules that have both carboxylic acids and nitrile groups in it? These two are going to be listed in the same part of the catalog if it's alphabetical listing of molecules. This 2 probably first in there. And you would say, oh, hey, it's 3 carbon group with carboxylic acid with the added nitrile group, sometimes on carbon 2, sometimes on carbon 3. And it kind of makes sense, I guess. Cool. All righty. That's it for the nitrile group. Oh, wait, I got 2 more examples. Just because, just more examples, more examples. Let's take away the C double bond O group. So I'm going to redraw this molecule, take away the double bond O, and I ask, okay, what's the name? Well, step 1, find the longest chain or ring with the most important functional group. We got nitrile versus alcohol. Yeah, the alcohol has 1 oxygen, but the nitrile group's got 2 pi bonds. And the pattern is more oxygen, more pi bond, more important. This one you might have to just remember. The nitrile group is really high on the list. It outranks the alcohol. So it's carbon 1 of the parent. Here's 2. And then I need to include the alcohol group on the parent. So don't go over here to 3, because then you have to add, somehow you have to identify, hey, the decoration to these 3 carbons is another carbon with an alcohol. That's going to make a complicated name. So try and include all your decorations on the parent, all the extra groups. The alcohol in this case is your extra group. Let's see, longest chain's 3, that's peanut or propane. The suffix is going to be nitrile. Ooh, so leave the E in there. On carbon 3 is hydroxy. Remember the prefix name for the alcohol group. And then also on the molecule is an extra methyl group on carbon 2. Okay, so then we want to alphabetize these, H before M. So we got 3-hydroxy, 2-methyl. Squeeze it in there. There it goes. You could have done better than that. There we go. 3-hydroxy, 2-methyl propane nitrile. Name of that molecule. And then what if we have this one? Okay, so this will be the last example. It's going way back to Unit 1, the special parent names. We got benzene with a carboxylic acid, oic acid, benzene and oic acid. Oh yeah, that's benzoic acid. And if you use benzoic acid, the carboxylic acid attaches to carbon 1 of the benzene ring. Go over here to 2, or the ortho position, and that's where the extra group, the cyano group, is located. Ortho-cyano benzoic acid or 2-cyano benzoic acid. Your choice. They both work. Ortho-metapara is allowed because we do have a benzene ring. Okay, those are all the examples. I think that those examples should handle anything you'll see in the homework or on an exam. So for out of the woods in terms of naming molecules, let's talk about how to make carboxylic acids. Well, we already have a head start. We actually know several ways of making carboxylic acids already. Back in Unit 1, we talked about alkyl side chains on benzene. So if we had alkanes, and if, let's redraw this molecule, methyl, 2 carbons is an ethyl group, and 1, 2, 3, 3 groups, 3 carbons rather. If you have a hydrogen on the carbon attached to the ring, then you have benzylic hydrogens, right? These are all benzylic. And K104 says, okay, the whole chain gets chopped off except for the benzylic carbon, which then becomes a carboxylic acid. And all 3 of these alkane side chains have benzylic hydrogens, so they're all oxidized. We can't add one equivalent and just get one of them to go. This is a crazy redox reaction, and it's, you can get a mixture of products. So just add enough KMNO4, oxidize all the side chains to carboxylic acids. Cool, that's one way to make a carboxylic acid if you have a benzene ring and an alkane side chain. More versatile method is if you have a primary alcohol, you can use a strong oxidizing agent, including KMNO4, but any of these others will work too. And wherever that C with alcohol currently is, we're just going to take away those H's and make a double bonded O. There we go. We make a carboxylic acid. So that's probably going to be the most popular one for synthesis problems because we get to start with alcohol groups. So if you need a carboxylic acid, one step with a strong oxidizer will take a primary alcohol to a carboxylic acid. Two other ways we've seen already. If you have an aldehyde, those strong oxidizers, these three should also be down here too. They all take aldehydes to carboxylic acids. Yeah, we talked about that several times, probably when we're discussing primary alcohols. Finally, go back to last semester. If you take an alkene or an alkyne, double or a triple bond, KMNO4, man, it's all over the place. That oxidatively cleaves the molecule. Remember the karate chop? So this is how I taught it in my class. I said, hey, KMNO4 does cleavage like a butcher's cleaving knife, chops the molecule in half like a big piece of meat, kind of bleeds a little bit. It's kind of morbid. But cut the double bond, chop right in half, copy, redraw the two halves of molecules, and they're bleeding a little bit. So take some cotton balls and stop the bleeding. And then this actually is an aldehyde group. And what do we say KMNO4 does to aldehydes? Oxidizes them to carboxylic acids. Ooh, and that's an aldehyde too. So they both get changed to the carboxylic acids. Triple bonds, kind of the same pattern. You chop it in the triple bond in half. Try and put a cotton ball on the end, but there's too much bleeding. Oxygen only bonds twice. So of the triple bond, oxygen can take away 2 bonds, but you need another cotton ball for the single bond. Hey, wait, oxygen, honk, 1, 2, 3, 4, wants 2 bonds. So, hey, oxygen, you're going to need a hydrogen. And that makes carboxylic acid. Yeah. So those are all great ways to make carboxylic acid if you need them. Again, I would favor the primary alcohol. That'll be the most versatile. Here's some new ways if those 4 ways aren't enough for you. Grignard, oh my goodness. Yes, Grignard reagents, they're very popular. They can do a whole bunch of things. They're like the Swiss Army knife of organic chemistry. Carboxylic acids from Grignards. How? Well, quick little review. What do we know about Grignard reagents? Well, take an alkyl halide, primary, secondary, tertiary. They can be vinyl. So you have a halide on an alkene or a halide on a benzene, that's aryl. They all work. Okay, so it's a very versatile reaction also. You can make a Grignard reagent. Let's just take propane with the bromine on carbon 1 to the Grignard. And then we said, hey, if you want a primary alcohol, use formaldehyde. If you want a secondary alcohol, use a different aldehyde, not formaldehyde. And if you want a tertiary alcohol, use a ketone or maybe an ester. Because in the mechanism, 2 arrows, the Grignard will bump up the pi bond. Redraw the ketone aldehyde or formaldehyde, the negatively charged oxygen there, and this carbon then attaches to this carbon, right? So these 3 carbons links together, and then every Grignard, you always have dilute acid, hydronium ion, so then afterwards, you can quench the negative charge. An acid-base reaction takes place, and I know it's a weirdly drawn tertiary alcohol, but that's the point. So how are we going to make a carboxylic acid? Well, the trick is to use dry ice. Quick aside, you still need to know the limitations of the Grignards. They're really versatile, really popular, doing lots of different chemistry, but they're not perfect, right? So there's 2 things, 2 big limitations. You can't have anything acidic on the molecule that you're creating a Grignard out of, because Grignard reagents are powerful bases and they'll yank the hydrogen off of any of these groups. Also, Grignard reagents like to bump up pi bonds. So on your molecule, so we're trying to make a Grignard reagent here, if somewhere else you have one of these other molecules, other functional groups, carbon, oxygen double bonds, then the Grignard from one of these molecules is going to attack the ketone of the other. And they're incompatible. Little DNE does not exist. Because you can't make this molecule. As you make them in a beaker, one Grignard will attack the other Grignard, and this molecule won't be in the solution for very long. Okay, let's focus on the acid part. And so the other functional group, not functional group, you also have to keep water out of here because Grignards are powerful bases, right? So this is helpful. This is where I was going with it. Remember Grignard's limitations. We need something dry, no water, but ice. What dry ice is actually the common name for solid CO2. Way back in general chemistry, I'm certain you've seen or had to draw the Lewis dot structure of carbon dioxide. And hey, there is a carbonyl group in there. So you follow the exact same pattern, the exact same mechanism. Beautiful. So if you want to make a carboxylic acid from a Grignard, pick any halide, aryl, vinyl, alkyl, iodide, chlorine or bromine. Fluorine doesn't work, remember. And mix it with magnesium metal to create your Grignard reagent. And then we're not making alcohols using formaldehyde, an aldehyde, or a ketone. We want a carboxylic acid. So bring in CO2. And you can just write CO2 over the arrow, but I want to show the mechanism. So let's draw CO2 vertically. And I'll focus on the top oxygen and say, hey, Grignard, go do this. And it says, sure, no problem. I'll bump up the pi bond. I'll hit this carbon and up goes the double bond O. Sorry, the pi bond onto that oxygen. So redraw. So that's what we did over here, right? We redrew the ketone and then we added the extra carbons. So let's do that. So redraw carboxylic acid, sorry, carbon dioxide. Pi bonds up here is a negative charge. And then 3 carbons. 1, 2, 3 from the Grignard. It's going to attach to the carbon of carbon dioxide. And then what do we do next? Well, exact same mechanisms what we're going to do. Add a dilute acid to quench this negative charge, and my face is in the way. Get out of the way. And we're going to do the same thing up here. Put a hydrogen on that negatively charged oxygen. So we got 4 carbons, double bond O, and this oxygen looks like an alcohol, but hey, it is not. It's a carboxylic acid. So you can draw it this way too. And there's all butanoic acid. It's going to smell at the lab like rancid microwave popcorn. Ew. Keep that in the fume hood. Nice. Okay, that's actually one of my favorite reactions. I've never done it. It'd be so easy. Just go down to Rayleigh's or Safeway and buy some dry ice. Wipe it off because it's going to collect moisture from the air. Clean it off as best you can. Break it up with a hammer and throw a piece in with your Grignard. I have to do that sometime. It'll be fun. Let's see, what else we need to know? Actually, we already know the mechanism, so just apply that old mechanism to this new reaction. Got the reagents, they're the same as before. We're just gonna substitute our aldehyde ketone with carbon dioxide, which in a weird way kind of resembles an aldehyde or a ketone. It's not though, but kind of reacts like one in the Grignard. And then remember your limitations. So if you want to review a discussion of these 2 limitations, one dealing with the base property of Grignards and the other one with the, bump up the pi bond, go back to Key Concepts Unit 1, Part 4. That's where it's discussed again in detail. Oh, and add to your list, the nitro group, nitrogen, oxygen there's a nitrogen oxygen double bond in the nitro group. So there's a Lewis dot structure. The sulfonic, it's not a sulfonic acid, it's got an R group. sulfonate group. The sulfur is double bonded to 2 oxygens. It's not showing up on the page with an R. So there's a double bond O here. And then the nitrile group, no double bond O, they react by Grignards. We might have to discuss that reaction today. Yeah, we'll get to that. Okay, that's a new way of making a carboxylic acid. It's a great way because Grignards are so common. You can make them from so many different things, but they're not perfect. So it'd be nice to have an alternate method. Yeah, well, we got 4. The best of those is oxidizing primary alcohols. Yeah, chemists, we're not satisfied with that. Hey, is there yet another new way? Yes, yes, there is. We can hydrolyze a nitrile. So what? Yeah, carboxylic acid and nitriles. You can take a nitrile and turn it into a carboxylic acid. So let's take this one, for example. And you can use an acid catalyst, hydronium ion. You have to heat it up. Sometimes you'll see a delta, a little triangle here, meaning heat. And oftentimes you don't. Not on my exams. You can hydrolyze it. This is a hydrolysis reaction. We're going to cut the triple bond, get rid of the nitrogen, and you turn it into a carboxylic acid. You can also do it by a base catalyzed route. Let's do this one. And you could use acid on this one too, but you have your choice. So I decided, okay, I'm gonna use a base catalyzed route. I used to use sodium hydroxide and water. And you also cut the triple bond end off and you create the carboxylic acid group here. Both work. There's no mechanism on the exam. However, I know some of you like mechanisms in the sense that it helps you remember and understand the reactions. So we're gonna talk about hydrolyzing amides in another video here in Unit 3. And I'll try to remember that in the hydrolysis reaction, the nitrile group is changed to an amide. And then we'll have the mechanism for hydrolysis amides. So it just makes for a very long mechanism. That's one reason why I'm not putting it on the exam. Okay, nitrile hydrolysis, really good way. The key though is, can you make the nitrile group? Can you put the nitrile group in your molecule? And usually nitriles are made by SN2 reactions, right? So my face is in the way yet again. Move that out of the way. So if you want this nitrile, that's not difficult. Start with 3 carbons and have a halide there. And by the old SN2 reaction, cyanide, Na+, C-, the nitrile's carbon will bump out the halide. But if it's SN2, only primary, secondary halides work. If you say, well, let's do here with NaCN, the answer is no, this is tertiary. You can't make this nitrile from a tertiary halide. No, no. That's a big limitation. And it comes from limitations of SN2 reactions. Okay, so what we have here are 2 really good methods of making carboxylic acids, the Grignard or nitriles. And if neither works, try one of these 4. But most of the time, one of these 2 will work. So there are homework questions, possibly an exam question, where it'll say, hey, we want to make a carboxylic acid, for example, maybe this one. Can you do it by the Grignard reagent carboxylation reaction sequence? Or can you do it by a nitrile hydrolysis reaction sequence? Choose the best method. So I need you to be familiar with these terms. Grignard reagent, carboxylation. To carboxylate means to add a carboxylic acid group. So Grignard reagent comes from halides. So what we're going to do is start here with the alkyl halide. And if you want to choose the Grignard reagent, well, take the alkyl halide, make a Grignard at it with magnesium. And I copied this off the internet. They elected to put the solvent in there. I usually leave it out on my exams. And then, yep, halide becomes a Grignard. Add carbon dioxide to make the well, in the mechanism, it's the anion of the carboxylic acid quench with hydronium ion to get your carboxylic acid. So this route works really well. Yay! But someone else might say, well, it's also a primary halide. Why don't I do an SN2 reaction with sodium cyanide, make the nitrile group, and then I'll hydrolyze it. And you notice up above, I use hydronium ion, but so does this author. Sulfuric with water makes hydronium. So they elected to show those reagents specifically for hydrolysis, acid hydrolysis, and they came up with the exact same carboxylic acid. And you might say, well, in this case, 2 steps are better than 3. Well, this last step is just dumping in some acid. You could choose either one. You can say both work. Yay! That's not always going to happen on the exam, though. So let's give some examples where you might be challenged in your choice of reaction. So, what if we say, let's make this one? Do you want to do it by the Grignard reagent? I'll try and stick to the same term so you know what type of problem I'm asking. Carboxylation or nitrile hydrolysis. Pick the best method, and it's usually a short answer question too. You show me the chemistry, but you also explain why one of these methods doesn't work, and be good to explain why the other one does. Well, then what are our choices? Well, right here is a carboxylic acid. So if you're going to attempt the Grignard, the C double bond O with an O used to be carbon dioxide. So that dot used to be carbon dioxide. We're doing a Grignard, so step 1, that looks so weird. I don't like it. All right, CO2. Same molecule, it just looks better. Step 1 of the Grignard reaction is add carbon dioxide. Step 2, every Grignard, quench it with acid. And then before that, let's see, this C is this C. So I have 1 carbon here with 3 methyls. I have 1 carbon with 3 methyls. Hey, that carbon's missing a bond. Yeah, because we're going to attach our Grignard. Bromine's my favorite halide. Maybe yours is iodide. Maybe it's chloride. They all work. You choose one. But this has to be made from the alkyl halide by magnesium. And then if it's a synthesis problem, no, that's not the question. We'll stop there. So do you start with this alkyl halide and go that way? Or maybe it's a nitrile reaction. Ew, let's take this one. Okay, oops. All right, so, or, how do we get there? Let's get rid of this, sorry. Anyways, okay, how do we do this? What, if we're doing the nitrile hydrolysis, the carbon that's currently a carboxylic acid used to be the triple bond N. And then this carbon is the next, so this carbon, the carboxylic acid, came from the nitrile. Hydrolysis chopped off the N and add the O's. And then to this carboxylic acid, we have 4 carbons. There's a center carbon. So to the nitrile group, there's a center carbon with 3 methyls coming off. So could you have started with this and added NaCN and just hydrolyze this? And your choice, you can use hydronium ion or you can use the base catalyzed route. They're both hydrolysis. Which one's best? Nope, not this one. Right? This is a tertiary halide, and we're attempting an SN2 reaction. So the Grignard wins. Yay! Is Grignard always going to win? No. So suppose we're trying to make You wouldn't have that though. I should have thought of something else. Oh, yeah, we can just do that. Suppose you're trying to make this molecule. Should you use the Grignard reagent carboxylation route? Or should you use nitrile hydrolysis? Well, the carboxylic acid, if you're using the Grignard, came from carbon dioxide and acid. This C is this C, so there should have been 2 carbons and an alcohol. And to this carbon, sorry, that's carboxylic acid, that's a carbon dioxide carbon. To this carbon, there used to be a Grignard. And then you make the Grignard from a halide. Wait, Grignard, hydrogen at the end of alcohol. No, they're incompatible. This one is not going to work. You can't do this. As you start to make the Grignard, one Grignard reaction, powerful base, is going to start stealing the hydrogen from the alcohol. You can get around this using a protecting group. So go back to Unit 1. I think we had that example where we could make a Grignard that originally had an alcohol group, but we used the, what do we use? Come on, brain. Oh, the silo group, the trimethyl silo group as our protecting group. Or abandon Grignard because of this hydrogen and try nitrile hydrolysis. Well, in nitrile hydrolysis, the carboxylic acid used to be a nitrile. So this carbon used to have a triple bond on it. And then we hydrolyze it with acid or base, your choice. And this is primary. So you had to be a little careful there. If you have a tertiary alcohol and you add acid, you can make alkenes out of that. Remember how it dehydrates? So it's primary, so it shouldn't work. On the other hand, you can just say, I'm going to avoid that altogether, and I will use a base catalyzed route. And now it's not going to react at all. Cool. All right. That's nice. If you left the acid on the exam, I would give you full credit because this is a primary alcohol. It should not dehydrate to form the alkene. And then now, how'd you get this nitrile group? Well, we used to have 2 carbons in the alcohol, and here was a halide. Bromine's my favorite. And then you're asking it to do an SN2 reaction. Alcohols are weak nucleophiles. This alcohol is not going to attack the primary halide, but nitrile is a great nucleophile. So yes, it's going to work just fine. This is the rel. Start with this halide with the alcohol in place. Add cyanide, get the SN2 reaction to work. It'll work just fine. And then use, I would prefer a base, but you can use acid hydrolysis. Go to carboxylic acid. That's the right route. Very cool. Okay, I think we're done talking about how to make carboxylic acids. Yeah, we're at the bottom of this side. Let's go up here to the right. Let's talk about nitriles. We also have a head start here. We've made nitriles before. So, oh my gosh, we just said so in the last 2 seconds ago. How do you make a nitrile group? Take an alkyl halide and add sodium cyanide by the SN2 reaction. Okay, that's going to be a very common and very good way of doing it. Yay, that works just fine. Also, last chapter, we could take an aldehyde or ketone and add HCN. Sometimes we would list the catalytic amount of sodium cyanide or potassium cyanide, and we get the cyanohydrin. So take double bond O, split it, keep O on one, and add the nitrile to the other leg, if you will. I don't know. There we go. There's our cyanohydrin. And hey, if you want to, you could hydrolyze this. I would do it by a base catalyzed route. Well, why am I even doing this? Just because. Sorry, put that in parentheses. We're trying to just stop making the two. We're just trying to make the nitrile group. Sorry, brain. Just one on a tangent there. If you use the acid-catalyzed route, this is a tertiary alcohol. It will dehydrate. So put that in parentheses too. So acid will break down the nitrile group, the carboxylic acid, but it will also dehydrate the alcohol and turn it into an alkene. Can't go this way with the double bond, the alkene, because that'll give this carbon 5 bonds. So you have to go over here or down here. Okay, two good ways of making nitrile groups, and then you can do more chemistry on it. More chemistry on it, right? We're going to hydrolyze that to carboxylic acid. All right. Big limitation though. Cyanohydrins, you can't make tertiary nitriles, right? So if you had formaldehyde and added HCN with or without the catalyst, then you'd have this, and this nitrile is connected to one carbon. If you had an aldehyde, nitrile is connected to 2 to 1. This is still one carbon. You don't do it that way. Yeah, so primary. Yeah, and then this one's, where's my other one? Oh, take that away. And the nitrile is connected to 2 carbons if you had a ketone. Anyways, how do you make this molecule? You can't do it by SN2, right? So if you want to attempt it, you'd say, hey, wherever there's a nitrile group, yeah, wherever there's a nitrile group, there used to be a halide. Yeah, but tertiary halides don't do SN2 reactions. You don't make this molecule. And you can't get this molecule from cyanohydrins. So what do? Well, you have to use this new way. You have to use an amide. And the trick is the amide has to be primary. What do we mean by that? Because I don't know if we classified amides yet. Amides, remember, are C double bond O with an N. So if you're asking to classify the degree of the amide, you talk to the nitrogen. A nitrogen atom, how many carbons are you attached to? And this nitrogen says 1, it's primary. This is a secondary amide. Hey, nitrogen, how many carbons are you attached to? I got the C double bond O on the left. I got 1 carbon down the left, and there's another carbon on my right on secondary. This is a tertiary amide. Yeah. Okay, this one's primary. Cool. So now use thionyl chloride, SOCl2. Yeah, so now we have 3 reactions. SOCl2 will make the halide. Oh, have you done this one yet? I want to say we've seen this one. We'll see it again later in Unit 3. Yeah, obviously, primary alcohol, tertiary alcohol, we're going to say they both get changed to the halides. But if you start with the carboxylic acid, you get the acid chloride. And now if you start with amide, primary amide, you make the nitrile. Wait, where'd the chlorine go? Yeah, it didn't do anything. It turns out this is a type of dehydration reaction. So if you're dehydrated, you've sweated out, you've lost all your water. So remove a water molecule. Remove this O and those 2 H's. Take away the water from this, and all you're left with C and N. Well, triple bond together so everyone's happy. Nitrogen wants 3 bonds, carbon wants 4. So thionyl chloride will dehydrate primary amides to give us a tertiary nitrile. And it turns out right now that's our only way to make tertiary nitriles, by this third and new way of synthesis. I'm not going to put the mechanism on the exam. What else? Oh, it's kind of quirky. Let's classify nitriles because it's weird. Okay, if you're going to classify the nitrile, you're going to follow the same pattern as if you're classifying halides or classifying alcohols or classifying, any other functional group pretty much. So, hey, bromine, what degree are you? Oh, it's shy. You got to talk to the carbon. Hey, carbon, what degree are you? Oh, this carbon says, well, I'm attached to one carbon over here. I'm primary. Bromine, you're also primary. Bromine, what's your degree? It's not talking. All right, talk to this carbon. It's attached carbon. Hey, carbon, what degree are you? Got one carbon up above. Doesn't matter if it's long chain or whatever. Directly attached. Hey, carbon, you have 4 bonds. Where are they? Well, one's to an H, one's to a bromine, one's to a C. The other the last fourth bond's to a C. Hey, I'm secondary. Yeah, and so is the bromine. Put a bunch of other groups out here. Who cares? Whatever. Benzene. What degree are you? Hey, carbon. There's a carbon, carbon, carbon. There's 3 carbons. You're tertiary. That should look familiar, right? Okay, we have to apply the same pattern to the nitrile. Hey, nitrile, what degree are you? Carbon. Why are you being bashful now? Because nitrogen's making it bashful. So go talk to this carbon. All right, carbon, what degree are you? Well, I got carbon on my left and I got the nitrile on my right. But I'm trying to classify nitrile. So you don't count this carbon. It's primary. That's weird. I know. But if you have an ethyl group with a bromine, it's pretty clearly primary. So if you swap out through an SN2 reaction, the nitrile for the halide, how does that change this carbonyl? It shouldn't. It should stay primary, just as if it was an alcohol or if it was iodide or something. These are all primary. So we're following the same pattern. We're not going to count this carbon. Sort of like what we did when we used the prefix cyano. We didn't count the carbon in the parent. This carbon, don't include the nitrile group. When you're classifying this carbon, it's secondary, making this a secondary nitrile. Same thing here. This carbon is attached to 1, 2, 3 carbons. Don't count that one. It's a tertiary nitrile. It's how we do things in organic chemistry. Sorry. Okay, done classifying. Last set of reactions, 3 of them? Yes. Okay, let's talk about changing nitriles and other things. Well, we also got a head start. We talked about hydrolysis. So if you have a nitrile, hydrolyze it. Acid or base. Use either one, and you'll get the carboxylic acid group. It's drawn upside down, sorry, but it's still a carboxylic acid group. That's one thing you can do with the nitrile, very popular way. You can also reduce it with a very powerful reducing agent. Let's take the same one. Okay, so lithium aluminum hydride. What do we know about that? We always follow up with acid. It's always a second reaction. We used that strong oxidize agent on aldehydes and ketones and carboxylic acids. And the pattern was, hey, the abbreviated mechanism, which is not entirely accurate, but it's enough to help us predict products, is we made the assumption, which is kind of incorrect, but hydride ion is supplied by lithium aluminum hydride. Hydride is a hydrogen with a lone pair, and it just bumps up the pi bond, sort of like a Grignard. Hydride's a powerful base. Grignard's a powerful base. They're both good nucleophiles in this type of nucleophilic addition reaction. Bump up the pi bond. This oxygen is now negative. This has a hydrogen. We talked about how the lone pair wants to come down, but then they have to kick out a carbon, a hydrogen, and they don't want to leave as negatively charged atoms, carbon, hydrogen. They're not electronegative. They can't stand that negative charge. They're powerful bases, powerful nucleophiles. So then it just waits for the H plus to come along. Hey, we made an alcohol. And the pattern is take away the pi bond, add an H to the O, and you're done. If you just have to predict the product. Not quite the same thing here. So what we do instead, no, it is the same pattern. What am I talking about? The pattern, double bond O, lose the pi bond, keep the single, and add H's. So the atom is happy, 1, 2, 3, 4. So let's just do the same thing. I'll check my notes, make sure I'm not messing up. Yeah. Right, so if we add an aldehyde, lithium, aluminum hydride, water, hydronium, recopy it. So took away the pi bond, add an H, so oxygen makes 2. Do the same thing, copy this, single bond to the end. Nitrogen wants 3 bonds, so add 2 H's. And we're done. Nice, cool. The mechanism is pretty straightforward. Again, it's a shortcut. It's very similar to this one. You're just going to do it twice. So we're in the mechanism. We're going to assume a lithium aluminum hydride supplies hydride ion. What does hydride do? It bumps up the pi bond. What does hydride do? It bumps up the pi bond. So do it. And if we keep track of nitrogen, a good Lewis dot structure has 8 dots. Nitrogen's making a triple bond. It would then have a lone pair. After hydrogen adds, 1 pi bond becomes a second lone pair of nitrogen. Hey, 2 bonds of nitrogen, 2 lone pairs gives it a negative charge. But it's going to happen twice. Another hydride comes along. Hey, lithium hydride had 4 of them. It's got plenty of H's to spare. Do it again. There's still 1 more pi bond, so bump up the pi bond. And now the nitrogen has 3 lone pairs. It's actually a -2 ion. Did I grab it? I did. Cool. And then the last step, add acid, quench this. Well, you could use water. It's such a powerful base, it wouldn't care. Add acid and the -2 and the +1, all 2 equivalents of hydronium. We'll put the hydrogens onto nitrogen and we get a primary amine. Yay. Chem majors, this is not the correct mechanism, but it's a great way of predicting products, and it's a mechanism that I'll give you full credit for on my exams. But you should have a feel that, really? We're going to create a -2 charge on nitrogen? The answer is no. So the aluminum is actually Lewis acid. After it uses 1 hydrogen, you're going to have aluminum hydride, which is neutral, but aluminum has an empty p orbital. It can actually do a Lewis acid base reaction and bind to a lone pair on nitrogen. And that'll give it another bond. It'll be to the aluminum, but it actually quenches the negative charge. And then the second hydrogen attaches to make a nitrogen, which has aluminum. And then it has the carbon. And what else am I missing? Oh, that's it. So actually just get a -1 charge. I'm not going to put that on the exam, but you can Google it, look it up now if you need the more accurate mechanism. Depends on your instructor. Last reaction, Grignard. Haven't we had enough of Grignard yet? No, we have not. Here it comes. Okay, what's going on here? Well, what did it do before? It bumped up the pi bonds. So we had our Grignard and these electrons bump up the pi bond, copy the ketone or aldehyde or formaldehyde or carbon dioxide, take away the pi bond, make the oxygen negative. The Grignard's carbons, wherever the Grignard was attached, that's your new point of attachment to the carbonyl carbon. And add H3O plus. And boom, we're done. We get a tertiary alcohol from a ketone. Yay. Do it with the nitrile. So let's take the same Grignard and let's add the triple bond in. And just like before, every Grignard, you follow up with acid. So at least that's a consistent pattern. And you get a point or a half a point for putting hydronium with your Grignard on exams. So it's kind of important. Okay, so what are we going to do? Well, same pattern. I'll show you the mechanism in a minute. You bump up the pi bond, so you think you have a double bond N. But if you have a double bond N, that's an amine. And in your second step, you're adding acid. Wait, acid reacts with amines. It's going to hydrolyze it. So yeah, you get a double bond end after reaction 1, the Grignard attacking, but reaction 2 comes and destroys, hydrolyzes the amine to make a carbonyl group. So this used to be an N. I'm following a pattern. Sorry, did I lose anyone? Okay, let's start over. It's a good idea to build off of something familiar. So let's review something we saw in Unit 2, ketones and Grignards, bump up the pi bond. So all we did was we copy the ketone. There's the 3 carbons of the ketone. And where we had double bond, now is a single bond. We have an O minus. Follow the same pattern. We had 3 carbons, and where we have a triple bond N, we're going to have a double bond N. Wait, nitrogen gets replaced by an oxygen. And then these 3 carbons get linked here, and we get the ketone product. And then some of us saying, Dennis, Grignards react with ketones. Doesn't that react again? No, the Grignard's gone. We don't get the ketone until we add the acid. And if there was any Grignard around, this acid would attack it and quench it. So there's definitely not any Grignard when the ketone starts being formed. Here, let's look at the mechanism. That I think will make more sense. Let's keep the title here. Okay. Got our Grignard. Let's actually draw in the C just to help us track what's happening. Okay, step 1 of the Grignard. Sometimes you can draw the resonance structure. Talked about that strategy back in Unit 1. This covalent bond between the carbon and the magnesium, you could draw the ionic form where carbon's negative. Magnesium then has a +2 charge, the bromine has a -1 charge. And the lone pair on carbon is the one that bumps up the pi bond. Or just say, hey, these 2 dots is this one line. This covalent bond is then used to connect this carbon to this carbon as it bumps up the pi bond up onto nitrogen. So let's copy the nitrile group, but lose the bond. If you want to track the lone pairs, nitrogen had 1, now it has 2, so it's a negative charge. And then these 3 carbons are then attached to the nitrogen. Oh, not that way. Let's zigzag it this way. There we go. These 2 are the same. If we're writing the mechanism, maybe we should track all our atoms. Where's the magnesium now? It used to be attached to this carbon right here, but now this carbon's neutral. Magnesium with the +2 is now attracted to that. Hey, the nitrogen's negative, so it's actually up here now. But it's still done. Reaction's over. If you use excess Grignard reagent, the nitrogen has a negative charge and it repels a second Grignard. Even though there's another pi bond that potentially could be reactive with the Grignard, it doesn't. It stops here, even if you use excess Grignard. So it's just sitting there. We're done. So now what? Well, start the second reaction. Add some acid. And the negative nitrogen with its low extra lone pair grabs an H+. Yeah, put that over here. And then I'll continue down here. And then you get water. Well, here we go. Carbon-nitrogen double bonds, the initial intermediate of this Grignard reaction, we get an amine. And unless you're using a burette and you're titrating this, which we don't, in a lab, we just add a whole bunch of acid. So we still have hydronium ions swimming around after the Grignard reaction finished. And so now what we got? We got amine looking at a whole bunch of hydronium ion. So now we're going to do the amine hydrolysis mechanism. And it might be helpful to see what our product is, right? So wherever the N, the double bond N used to be, initially we had a double bond O. We're going to have this ketone. Oh, by the way, that was the product of the reaction up here, right? This ketone had 1, 2, 3, 4, 5, 6 carbons, and on carbon 3, there was a ketone group. Let's see, 1, 2, 3, 4, 5, 6. Yep, carbon 3 has a ketone group. So let's just hydrolyze it. So I know it makes for a long mechanism. We already got 2 steps up here. This is why chemistry builds on itself. So before you might even want to pause the video now, before you go on, review the amine hydrolysis mechanism, because we're going to need it in Unit 3. Okay, so what do we do? One idea is to go ahead and go the forward direction. How do you make this amine from a ketone? Well, you use a primary amine. Well, where's the nitrogen's carbon? It doesn't have any. You actually use ammonia. So amine formation or amine synthesis, to make this amine, we're going to start with ammonia and this ketone. And the mechanism starts out with ammonia being a good nucleophile, SN2 reactions. Strong bases are good nucleophiles, and SN2. SN stands for sulfur and nitrogen. So we bump up the pi bond. Nitrogen carries its 3 carbons along, now has 4 bonds. We say, hey, lone pair on the oxygen, go grab an H+. Opposites attract. Whoops, I added an extra carbon, didn't I? Darn it. Let's keep this eraser handy. At least I caught my mistake now. There we go, everything's neutral. I pause here and say, wait, am I done? Everybody's neutral, got their hunk. Correct number of bonds. Oh wait, no. If you're adding a primary amine to a ketone, you're trying to make an amine. Double bond N. I need a double bond here. So I need to get rid of one of these H's. I need this whole group to leave, and OH minus can't leave now. It needs some help. Bring in the acid catalyst, right? So amine formation requires an acid catalyst. It's just weird that the acid doesn't react first like all our other acid catalyzed reactions do. Amine. Very weird, but actually pretty important. Okay, hydronium turned into water. I'm good. All right, so what do we want? We want a double bond. So lone pair of nitrogen, go make double bond, and at the same time kick out the water. Good, good idea. Or, you can leave this. I'll give you full credit on the exam, but the bond angle really bugs me. So what if we swing this double bond group up here? You don't have to do that. I'm just going to redraw this molecule. So my bond angles are 120 now because this carbon's sp2 hybridized. That double bond, right? Okay, these two are the same. What happened? We kicked out a water molecule, so it's still there. And then we're trying to make that thing. What was it? Let's go back up. Yeah, we're trying to make the amine. And so the last step is water is a base that removes H+, and we have our amine. Yay, we're done. Oh, wait, is that what we're supposed to do? No, we're supposed to draw the amine hydrolysis mechanism. Okay, but remember that's a strategy. One strategy that works really well. If you got the forward mechanism memorized for making an amine, go ahead and map it out as I did. And then go and erase your arrows. So eraser. So let's take this out. Erase all your curved arrows. And actually, can I pause the video? Yes, yes, I can pause the video. Erase all those curved arrows and then write start here and go this way. So these two molecules are these molecules up here. That there's a double bond in hiding under there. Let's show it. I'm a visual learner. I need to see it. There we go. Right. So that's a amine. Amine with hydronium. Amine, hydronium. I want to show the mechanism. So I'm going to do it now. Starting here, these two molecules must turn into these molecules. What changed? Nitrogen has an H. Hydronium lost an H. Oh, nitrogen, go grab that H. And now you're this molecule, and hydronium turns in the water. Cool. Got these two molecules, well, same as this one. This molecule becomes this molecule. How? All the water added to it. This water. These add here, right? So attach the water to this top carbon. Good. Nitrogen ends up with a single bond. Oh yeah, bump up the pi bond. And we got that molecule. Okay, this molecule has to turn into this molecule. How? Let's see. The O had two H's. Now it only has one. Nitrogen, no change. Cool. This water molecule is sitting here. Why is that? Oh, because it's going to pick up the H. The oxygen loses an H to this one. So, hey, oxygen from water, go grab that hydrogen for me. Thank you. And we got this structure then. Pull off that H. Redraw this molecule. It's going to look like that. Nice. All right, this molecule's got to turn to this one. We're just sliding the hydrogen over. So this H goes down here, but the curved arrow says where the electrons are going. Lone pair, go grab that H. Yank that hydrogen over here to the nitrogen. Good. We're done, at least from that step. Last step to go here, because we're going to end here. This is our product, the ketone product of the amine Grignard reaction, or the nitrile Grignard reaction. How do you go from here to there? This nitrogen's got to clip away. So those electrons go on the nitrogen so it can have its lone pair back. Hey, lone pair of the oxygen, fall down, make the double bond. And we're done. Sweet. Whew. Okay. Yeah, is that the world record so far in terms of longest mechanism? Might be. Don't think of it that way. Sorry I even mentioned it. Think of it as two mechanisms that you already know. And if you don't know them, go back and review them. So back in Unit 1, we talked about Grignards reacting with carbonyls to bump up the pi bond. That's not too bad. 2 arrows, 1 step, second arrow, second step, we're done. Do the exact same thing with the nitrile. 2 arrows, 1 step, second arrow, we're done. No, we're not. Then you have to go back and review how to hydrolyze an amine. So that's in Unit 2. But again, if you know those two mechanisms, you just link them together, and now you have this new reaction, the Grignard reactions with nitriles. Okay, let's take a break. I'll see you in the next video.